In this video, we'll perform the exercises of the lesson 7 from Nordic Semiconductor Academy, which is about multi-threaded applications. Before following the exercises, you should check the technical information provided in the beginning of the lesson. It gives you a nice understanding of the difference between the bare metal and RTOS real-time OS applications, the definitions of threads, and in which states they can be. And also we'll speak about the system threads, user-created threads, and work queue threads. There are always two threads spawned by default, the main thread and the idle thread. I made an addition to the exercises with a main function. It will create a counter to help us observe the outputs on the Thingy:91, since we cannot connect to the device with a serial terminal as soon as it's turned on. User-created threads will be our main focus, and how to handle threads with the same priority will be an important topic, and we'll see how the work queue thread is used to offload non-urgent work from an ISR or a high priority thread to a lower priority thread. This is the definition and the demonstration of the work queue thread. You can see that the ISR or the higher priority thread submits the work to the work queue, and the thread pulls the item from the queue in a FIFO order. And the scheduler can be seen as the maestro which assigns CPU time to a thread according to its scheduling algorithm. And in this note, you can see that the number of running threads is limited to the application cores of the device you are using. Here in the example, it says that the NRF52840 has one application core, allowing to run one thread at a time. And since the Zephyr RTOS is a tickless RTOS, the scheduler is woken up based on events known as rescheduler points. And here there are examples of rescheduling points, which we will see in our exercises. For example, k_yield, or using semaphores or mutexes. Now let's continue with exercise 1, thread creation and priorities. Here we will see how two threads can affect one another with their priorities. And you will see that k_thread_define macro is used for the definition of the threads. You can see its parameters in the list: name, stack size, entry, and etc. We will enter some values for those, and we will leave some of them blank. You can click on this link to see the Zephyr documentation. And this is the GitHub repository for this exercise. You can go to lesson 7, and this is exercise 1. I cloned this directory to my local folder, so I'll be using it with Visual Studio Code. So let's open Visual Studio Code, and let's first check our folder. It's right here. Now we can open Visual Studio Code, and we are going to add an existing application, and we will point to our directory, which is Fundamental Lesson 7 Exercise 1. And you can see the content of it. Project.conf main.c. You can see that two threads are defined in the template, and we will fill in the necessary places. First, we will define the stack sizes and also the priorities of the two threads. We will define both as 7 priority. It doesn't matter if it's 7 or 6. What matters is they need to be equal to each other, because we will observe what will happen when two of them have same priorities. So the stack size should be power of 2. Here it mentions that, but in actual deployment you should carefully define the stack size. And as I mentioned, two of the threads, both threads have same priority. And in the thread we will do nothing but print a message just to indicate which thread is running at that time. So let's add this one for thread 1. It will say that hello, I'm thread 1. So let's replace this 0 with 1. And in the thread 0, we will paste the same one, only with thread 0. So the threads won't be yielding or they won't be sleeping, so they will be always in the runnable state, and we will see what will happen. So we will use these k underscore thread underscore define for defining the two threads. So we'll add it on the mentioned step at the end of code. So they have the same priority, same stack size, but their functions are, one is thread 0, the other is thread 1. So we will be building the application. We won't be doing any updates after this. So we can go to add build configuration, and our Thingy91 is selected, and we can build our configuration. Now let's load this configuration to our Thingy91 device. So first let's put it into DFU mode, and then let's open NRF Connect for desktop, and we will open the programmer tool, and we will select our Thingy91 device. We will choose our file app underscore sign.txt in the Zephyr folder, in the build Zephyr folder, and we will write this code to our device. Once it's finished, we can open PuTTY. Our device is at COM7. Default speed is 115, 200. And once we turn on our device, we will be able to connect to it via the serial terminal. And you can see that we can only see thread 0 in the terminal. Let's restart PuTTY once again. We will again see the thread 0. We will not be able to see thread 1 because none of the threads are yielding or sleeping. Now I will make an addition to this exercise, and I will add this main function. Because the main thread has the highest priority, it has priority 0, and it's going to run before all the other threads. So, and by this main function, I'll be able to add some delay. So it's going to count up to 1,000, and then it's going to run the other threads as we programmed our device. Okay, so let's put the device in DFU mode first, so that we will be able to load this code. Let's select our device, choose our code, and we will click on write to write our code. Why I'm adding this main function is, as soon as we turn on the Thingy91, we are not able to see the serial monitor via PuTTY or any other terminal, because it takes some time after we turn it on, and we will be able to connect to the device. So I'm going to turn the device on and start the session. As you can see that it counted up to 1,000, then it started saying hello, I'm thread 0. We will see why only thread 0 is being printed out. You can see it in the documentation as well. Our buffer is not enough, so I'm going to enable logging, so we will be able to see all the session once we turn PuTTY on. So let's turn off and on the device once again. Turn it off. Again, I will make the restart session ready. So as soon as I turn it on, I'm going to click on restart session. And as you can see, it counted up to 1,000 and then said, hello, I'm thread 0. Now let's turn off the device and see the log, you can see that we could catch it from 284. So we had turned on the device, it counted up to 284, then we enabled the serial session. As you can see, after 1000, it starts saying hello, I'm thread 0. The reason we were not seeing thread 1 but only thread 0 in the log was that none of the threads were yielding or none of them were sleeping after they executed. So let's run the function k_yield for thread 0 and let's build our application once again to see its effects. Now we can put our device in DFU mode and we will load our code to the device. And we'll click on write once again. And now it's loaded on our device. Let's open PuTTY. And let's enable logging as well. Let's reset the terminal. Let's turn on our device and click on restart session. So you can see that it counted up to 1000, but we can not see in this buffer whether we saw thread 0. So let's go to our log. So it's going to count up to 1000, and then we will see thread 0 only for once. That's expected. Yes, we are only seeing thread 0 once, and then it yields and thread 1 continues to run. So now let's use k_yield for thread 1 as well. So both threads will yield after they execute, actually after they print saying hello, I'm thread 0 or hello, I'm thread 1. So let's build our application with this. Once the build is finished, we can load it to our device once again, putting it into DFU mode, selecting our device, selecting our code. It's app_.hex, signed.hex. Click on write once again to upload it. Now, since it's uploaded, we can open PuTTY. Let's reset terminal, turn the device on and off. We can turn it off and on, and we will restart the session. Unfortunately, I was not that quick, so you can see that once we run our code, thread 0 is running and then it's yielding, and then thread 1. So the scheduler goes in between these two threads. You can check it from the log as well. So this is the previous configuration we appended to our log, and you can see that this is the last section. If we scroll down, yes, so it switches between thread 0 and thread 1. We can have a better look. We will repeat the process. while the device is turned off, we don't have any COM ports. That's the reason we are having problems. That's the reason I'm adding some delay in the beginning. So we can check this one better. I guess we will have a better look. So let's turn it off and let's open code, the log, sorry. You can see that it's going to count up to 1,000, then it starts with thread 0 and then thread 1, and it switches in between these two. Now we will change the k yield. We will delete them in both threads and we will use k underscore msleep, and we will specify a duration of 5 milliseconds. So it will have a similar effect, but there is a difference in between using k yield and also k msleep or k sleep. During the loading of the code, I can describe you the difference in between these two. So if you are using k yield, this is going to change the thread states from running to runnable. So at the next rescheduling point, the thread that just yielded is still a candidate in the scheduler's algorithm. So this is the description I took from academy.nordic7.com. And also if you use k underscore sleep or k underscore msleep for milliseconds, this is going to change the thread states from running to non-runnable until the timeout has passed. So if you specify 5 milliseconds, the thread will be in non-runnable state in 5 milliseconds, and after that it will be runnable. So you can choose in between k yield and k msleep according to your preference and according to your plan. So here we can see the log. I increased the counter to 2000. So after 2000, the main thread is going to stop because main thread is going to run only for once. Then thread 0, thread 1, thread 0, and thread 1 will run. Now we will go to exercise 2, in which we will use time slicing. So the threads won't be yielding or won't be using kmsleep. So this is the link to the GitHub repository. We are going to use lesson 7 exercise 2. So you can clone it into your local folder. I've done it already. So I have it here in fundamentals lesson 7 exercise 2. So I'm going to open Visual Studio Code and add an existing application from the welcome page and choose the folder. I will dismiss these messages. So I'll go to my folder. You can see that this is the main.c and we have project.conf, and we will make some changes in project.conf. The threads priorities are the same. They are printing hello, I'm thread 0 or hello, I'm thread 1. They don't yield or sleep. So we know that from the previous exercises that one will block the other. But once we enable time slicing with config time slicing is equal to yes, time slicing size and time slice priority, we will be able to implement time slicing. Let's paste these 3 lines here. So time slice size says that after 10 milliseconds, it will switch to the other available thread, okay? So we will build our application and then we are going to load it to our Thingy91 device. Let's add build configuration. Our device is chosen and we will click on build configuration. Now that the build is complete, we will put our device in DFU mode and we will select our device. And then we are going to choose our file. This time lesson 7 exercise 2 build vir app underscore sign.x. However, we had a conflict here, so let's click on clear files. Choose once again. This is the correct folder, okay. Now we can click on write. We can click on write once again to load the code to the device. Now let's open PuTTY and observe the output of time slicing. You can see that we see thread 0 and thread 1. And we can see it in the log as well. Now we are going to increase the priority of thread 0 to 6. So it will be a higher priority than thread 1. What we are expecting is the thread 0 will always run since we are using time slicing. However, it will work for threads of the same priority. So let's build our application and load it to Thingy91. We'll select our device. app_sign.hex. Click on write and write once again. And we will open PuTTY and we will turn our device off and on. Turn the device on. Let's click on restart session. We can see that we only see thread 0 and thread 1 is starving for CPU time because it has lower priority. Now in exercise 3 we are going to be using a work queue and we will see how to create it. But before that, let's add an existing application and use the template from lesson 7 exercise 3, which we cloned from GitHub page of Nordic. And let's check the content of it. In the source we have our main.c file and we have the project.conf file. You can see that the stack sizes are defined and also thread 0 and thread 1 is also defined. In the documentation it says that thread 1 will be copied and pasted, but that's not the case. So first we add the priorities. Thread 0 will have the highest priority. Thread 1 will have a lower priority and the lowest priority will be for the work queue. So let's copy this section and paste it in the related field, step 2, and paste it here. Okay, now we have defined the priorities. And as you can see here, thread 0 is already included in the code. So what it does is explained here. So it's going to run some emulate work function and it's going to measure the time that it spends for that, and it's going to sleep for 20 milliseconds. And thread 0, as I mentioned, has a higher priority. You can see the description here. And thread 1 is exactly the same. However, you know that it has a lower priority and it's already included in the code, so we don't have to paste anything for thread 1. It also sleeps for 20 milliseconds. As you can see, it has this function emulate_work. We have to define that. We will paste it, copy it from step 5, an inline function to emulate work. So it's going to count up to 150,000. So, and there you have an explanation that it takes 24 milliseconds for a specific system on a chip. Adds for nRF50 to 840. And we are going to build our application. So we will add a build configuration for this project. Lesson 7 exercise 3. We are going to choose our board and we will click on build configuration. Now that we have our build, we are going to flash it to our Thingy:91 device using the programmer tool. So we are going to set our device in DFU mode. We are going to select our device, Thingy:91, and then we are going to select our code, app_sign.x. This is the thing that we did for many times, also in this exercise as well. So we will choose app_sign.x and we will click on write to flash it to our Thingy:91. Once it's flashed, we can open PuTTY and turn our device off and on to have the logs. So we are going to turn the device off and on, and then I'm going to click on open, and we will be able to see the outputs of the print key. So I'm going to turn the device off to analyze it better. You will see that thread 0, which has the higher priority, is executed in about 26 seconds, and thread 1, which has lower priority than thread 0, is executed at about 54 seconds. Okay, so we will see that this is also aligned with the expected output from Nordic Academy's website. And let's understand the reason for this. Why thread 0 is executed. Seems that it's executed twice, one after the other, and then thread 1 is executed. Actually, that's not the case. Thread 1 is finishing its job in 56 milliseconds, etc. So you will see it much better in the timeline. You will see that thread 0, which has higher priority, is executed about 26 milliseconds, and then it goes to sleep for 20 milliseconds. Thread 1 is executed since thread 0 cannot be run at that time. Once 20 milliseconds is finished, thread 0 comes back once again and it's executed once again, and then we are going to leave the thread 1, the remaining part of thread 1. So in total, thread 1 takes about 56 milliseconds. In this last section of the exercise, we are going to use the work queue thread in order to offload the work from thread 0. So what we are going to do is paste this section to step 7, which creates this work info and also the offload function. And in thread 0, we are going to be adding this section for initiating the work queue. So let's go to thread 0 under step 8. Let's paste this section. And we will not be using emulate work, but we will be using this k work submit to queue, and we will comment out emulate work. And we are going to build our application with this configuration. Once the build is complete, we can flash this code to our Thingy:91. Let's put it in DFU mode first and then select it, write our hex file. Right, once again to flash it on the device. Now we will be able to see the logs. Let's open PuTTY, turn the device off and on, so we can turn off the device to examine the log carefully. You see that thread 0 is taking less than 1 millisecond, so we see it as yielding this round in 0 milliseconds, and thread 1 takes about 29 milliseconds, which is far less than the previous configuration. So we can see why this is the situation. This is a better way of using the resources. So what we are having is the thread 0 is being executed in less than 1 millisecond. Then the scheduler goes to thread 1, and then after thread 1 sleeps, the work thread is selected by the scheduler so that both thread 1 and thread 0 take a lot less time than the previous configuration.